So I'm going to speak in English. It's not my mother tongue. I'm Danish by birth, but I've lived some years in London, and I worked on an international project for the vast of my career. Yeah. First of all, thank you for inviting me here today. It's getting late, so I hope you don't fall asleep while I speak. Yeah. And if you do have questions, please ask me. You know, it's supposed to be a dialogue, not just me passing on what I've done. So I'm going to talk about digital design and like how do we get from design to manufacture, yeah? Because this is really one of the challenges, you know, with the complex geometry and BIM. How do we then actually start to manufacturing the products at the end of the day, yeah? And I've been working for many years for contractors and also now for consultants, thinking about how we get that step and when we have complex projects, yeah? So I'm going to talk a bit about MOTT MACDONALD. You know, we are a global engineering company, so throughout the world. We do management development projects as well. And we cover a lot of different subjects, which is very important, because today everything is interlinked. Yeah? And just an example is about, you know, smart grid, which is you're going to see in the future, about batteries and batteries in homes, and how we start developing, you know, storage energy in the houses and all these things, and they start to be connected to all the other parts of engineering we're doing. Yeah. So having being in a company who covers a lot of different sectors means that you can have a holistic approach to building design, which is very important in the future. Yeah? I don't believe that we can keep doing separate engineering as we did in the past. We really have to start thinking about how we combine things in the future. Yeah. So, of course, one of these things with being in a global company is about connected thinking, and, you know, and finding, you know, solutions to problems is very important. Yeah. I'm going to stop talking about our company very, very soon. Connected thinking, and this is really what this is about, and how we globally, because one of the things we see, and I've spoke about this earlier today, is that how do we share knowledge? Yeah. And a lot when we meet clients is that what in the end they pay for is risk and somebody to take the risk. Yeah? And what we want to make sure is that we're not all just risk managers, but we actually like add value to the clients by sharing our knowledge or like solving problems for them. But when you are in a global company, you have people sitting all over the world which has different specialities, and it's very important that you bring that knowledge to that client who needs it in real time. Yeah? And this is what this is all about. And I think we need to do more of this, and this is what I'm going to talk about when we come to the digital design and how we share knowledge. Yeah? Because everything today is apps, and the companies who kind of try to close their knowledge in, they will probably not survive because the open platform software is the one that goes so fast and develops faster. It's like Uber. Why is Uber now the biggest taxi companies in the world? Yeah, like who would have thought about that 10 years ago? Okay, so we are throughout the world. We even have an office in Istanbul, which is really good and great. But predominantly we are in Europe. Yeah. Okay, so not more about MOTT MACDONALD. I'm going to talk about building design and about how we have changed the building design in the last 50 years and how they're probably going to look like in the next 40 years as well. Yeah. So when I talk to some of the junior people in MOTT MACDONALD who starts right now, I said that the buildings that they are going to design today, they're going to be used for 50 years. Yeah. So it's very important that they understand the consequences of new technology into buildings. Yeah. And also, so when we start looking into the future, they will probably be designing some of these buildings that we are foreseeing in the future. So we need to understand a bit, you know, what kind of technology do we need to have to be able to develop this in the future. Yeah? Okay, building design. And of course, when we look at art and art projects, this is some of the most glamorous projects. I worked on a lot of them, but you know Gary, like who took over from like Guggenheim was the first, and of course Frank Lloyd Wright, but the latest Guggenheim, we're going to come to them. Mies van der Rohe, the Barbican Center in London, and then we move on to some of the newer ones, and you see Gary, which have done the most complicated design. And this is what I'm going to talk a bit about today, because this is what I do. It's like, how do you design these buildings? Yeah. But we understand the complexity, and you know, the reason why we have these new buildings is because the technology, digital design, has made it possible to do these buildings. Yeah? And but one of the challenges is that when we look at these buildings, how are we actually going to manufacture these individual panels? Yeah? So, how do the buildings going to look like in the future? It's a very important question to ask, yeah? Because it's what's going to drive the technology we have, and especially in the delivery industry, looking at, what kind of machines do we need to have, what kind of knowledge do we need to have, and so on and so forth. Yeah? So if you look in 10 years' time, or maybe 20 years' time, this is the buildings that are going to be maybe much more organic. This, of course, we are now looking into a crystal ball, and I'm not sure the future is actually going to look like this. One of the things we know from now is that these complex geometry buildings, organic buildings, you can call them, are very expensive. Yeah? And when you start trying to price these very complicated panels, and I'm sure there's a lot of panel manufacturers in here that say, what is the price difference for a flat panel towards one which is freeform, doubly curved? Yeah? And then, the client says, well, I want it for the same price as the flat one. It's not going to happen. Yeah? So we need to try to understand, and maybe in the future, with the technology we have, the price is going to be the same. You can do a flat panel the same as you can do a complex geometry one because you're just going to print it. And this is where we need to understand, where is technology taking us? Huh? And what are the requirements we need for the buildings? Not just the visual look, but also the performance requirements into the buildings. Yeah? Okay. In 30 years, and especially in 40 years, we're going to have maybe, hopefully, zero carbon buildings, where everything is integrated into the buildings, and there's going to be maybe small cities. Yeah? We know that the numbers of cities we have today is going to be doubled in the next 30 years. So we need to build just as many cities we have today in the next 30 years to be able to meet the demands of urbanization. Yeah? So that's going to be a big challenge for the industry, and we need to have the technology available to be able to meet these demands. Yeah? It's also the other thing, how many people actually study engineering today? And how do we attract young people to be engineers, not just bankers or developers or working in other industries? Yeah? How do we get the most clever people into the building industry and encourage them really to start doing these things because it's important for us? Yeah? And we have a big shortage of very good structural engineers in Europe at the moment because they choose not to study engineering, or structural engineering at least. Yeah? Okay. But I think just going over this, sustainability and smart cities, I think this is where we're going to go. But to develop this, we still need to take a further step forward. Yeah? And this is what I'm going to show a bit when I get to the later part of the presentation. So, when we look at architecture students today, what are they designing? This is very important because they are the new generation. They're the people who's going to actually do these things, and they're very much inspired by Zaha Hadid and free-form shaping. They're looking into to digital printing and all these things. So these things will come, and there'll be more and more. There'll be a demand for this. The big question, of course, is always, can the client afford to pay for these buildings? Yeah? And that's going to be the interesting question to answer. Okay, so taking a step back and looking at complex geometry before there was anything called a computer. This is Gaudi. This is Sagrada La Familia in Barcelona. I don't know if you've seen it. What is very important about this is that for almost 70 years, people didn't really know how Gaudi actually designed the geometry into the building. They then find out, I think, in 1975, and then after that they've been able to continue because all the drawings and all these things was lost. Yeah? And this is very important. But at least you look at something this beautiful and done without a computer. But of course, it's very expensive. It's taken more than 100 years to build the church. And the question is, with the digital design today, can we actually move on? Can we do things faster and better and cheaper? Yeah? Because the demand is there. Okay. So this slide here is something I've done in my research, looking at how do you get from an architectural form down to the installation. And some of the issues there is bridging the gaps between each of these levels, yeah? Which is very important. So when you do an organic form, the architect says, this is what I like, and the client says, well, I would like that as well, I would pay for it. The question is then, how do you then start actually making it into a building? The first line of geometry, and the big question, and this is the question today about, BIM. Can you do BIM on a building like this? Is it possible? And then, again, the last thing is, how do we then going to manufacture the panels? So what I've shown is like the layers, the first architectural form. The next one is the optimization of the panels itself. So if you've seen architects, when they work with these freeform shapes, the line is a line, but it's actually not a space. So when you start adding like a space in between the panels and you start offsetting them, and especially when they're complex geometry, suddenly the panels becomes very complicated. Yeah? And if you start saying, okay, well, they also have a weight, and everybody who works with concrete, and I know this from Fiberbeton here, they know that when we start adding thickness to the panels, and especially if they're very big, you get more and more thickness because they have to span longer, and then suddenly you run out of space, yeah? And then you can't build a building, yeah? And then you need to turn to another material. And this is what happened on at least 2 buildings I worked on. One was the one in Baku, the Heidi Aliyev Center. It was designed with concrete, but it's been built in plastic, so glass fiber reinforced plastic. And everybody knows it's flammable and it burns. And it actually did burn. But this is because the panels became so complex and so heavy that they couldn't do it. Yeah? So this is about taking digital design and then making it into something which can be manufactured and priced and paid for by the client is very complicated. And also some of these elements becomes bigger and bigger. Then there are restrictions in transportation and installation and sequencing and all these things. And I think it's very important to start thinking about these things and understanding. And there I've not talked about the different programs that the different levels of, the architect works in one program, the optimization engineers work in a secondary program, then the production is a third one, yeah, and then we start talking about an installation, maybe this is a fourth program, yeah? And the question is, how do all these programs speak together, yeah? And do we need to have one digital language, yeah? And how do you control all this in the future? This is going to be one of the big questions when you take these on. And we see this already now, that you actually have mistakes happening, and then for some odd reason, program A didn't speak properly to program B, and then the things have different shapes when they come to site, and then they don't fit in, which can be a nightmare. Yeah? Anyway, talking about digital design, and digital optimization, which is really important, and the technologies behind it. Recently been working on this project here to take a shell and then make it cheaper and better, yeah? And by using cold deformed glass instead of adding a second layer of aluminium, yeah? So, but the geometry was so complex, it's not a solution so obvious for it, yeah? And you can see the two different solutions. The first one was the one from the architect. The second one was a proposal which we came up with. And the difference is that the kink angles in the panels, in the first one is 200 millimeters. Yeah, means it's almost impossible to deal with that kink angle. And if you want to make it watertight, it's almost not a solution. The second one is where you take a flat piece of glass and you bend it down. But to go from A to B, you had to do an optimization of the geometry. Yeah. And how do you do that? And you do that by, of course, using very complex mathematics. Yeah? And this is why we start working, mathematicians start to work with engineers and with architects to come up with more slim solutions. Yeah? One of the things we then did is because, and this is one of these problems, and also for the industry, is that you come up with a value engineering solution, and then the client says, well, I would like to see your files, your digital files. And this is where we said, well, you can see our file, but we're not going to give it to you. So what we did is that we made this model, we put it up in the cloud, we just sent a link to the client and said, you can go look at the geometry, but we're not going to give it to you. Because if we give them the geometry, they don't need us anymore. Yeah? So we said, well, here it is, and we are still waiting for the final decision whether or not we're going to win and get to build this dome. But it's this about intellectual property and these 3D digital models, because there's so much embedded knowledge into it. We need to think about how we protect ourselves. Yeah? And I've been a contractor for 10 years of my life, and I know what it means when you spend like thousands and thousands of euros on a bid, And then the client says, well, thank you very much, your best ideas I take, and then I go over to somebody who's cheaper, and then you lost. Yeah? And this is something we need to think about when we work in digital design. Yeah? Because if it's just going to be like that, then some companies will not survive, and there won't be any companies who have great ideas, yeah? And they're just going to disappear. Yeah? Okay, moving on. Talking about digital design and complex geometry. This is probably one of the most complicated buildings I've worked on. When I looked at it first time, this is for the Lego family. I'm sure you know Lego. Yeah? So this is a private building. This is their private investment fund for Lego they have in Denmark. And when I looked at this first time, and it was an artist who's designing the building, not an architect. Yeah? So this is the first. This is when you need to understand that this is going to be difficult. Yeah? Because there are different standards of complexity. But when I looked at this first time, I said, that's not really for me. There's not much glass. It's all brick. I don't do brick. I only do glass and steel. Yeah. So But then they really asked me, Thomas, have a look. And then I start looking, all the glass there, they are all conical elliptical. Yeah. And they start as a circle and end up as an ellipse. Yeah. And all the glass is then conical elliptical. And we start looking at the steel frames. Yeah. The steel frames, they look really simple, but when you start really looking at them and saying, how are we going to manufacture them, it starts to become very complex. Yeah? And this is, again, understanding digital design. You look at this, you try to price it. Yeah? This facade here, it ended up costing 10,000 euros per square meter, which is the most expensive facade I've ever done. I'm going to go a bit further, but this is about understanding complexity. And then, because when you have an artist or an architect who start doing interesting shapes, how are you going to price it? And because there's on this building, there was no earlier, nobody has done it before. So a lot of people put a lot of risk on the table trying to price this. And I know that the company I work for, they're just going to break even if they're lucky. Yeah? And the client, of course, he says, well, I don't want to pay for a lot of risk. Yeah? So this is some of the consequences into complex geometry and the freeform tools which people have available. They can just design anything. Yeah? Okay, moving on a bit. Another project I've done which has been realized, which is a pure glass structure. But the reason why I'm going to talk about this is about how was this cloud actually produced, and I'm going to come back to this in a bit. Yeah? So the glass, and if you ever get to Manchester, go and look at it. It's an amazing building. So the roof is 27 tons, and it just stands on 20 glass columns or walls. There's no steel, and there's almost no bracing of the glass, so there's no glass fins in behind. I really recommend you to go and have a look at it. Yeah? So it's a big monocoque. It's made like a ship, mirror polished stainless steel. But I'm going to talk about some of the challenges, about manufacturing the bottom side of this panel here, yeah? And also how fast you actually need to do it to take a concept into actually delivering it. Yeah. Okay. So, taking a step back, because the things we're also going to talk about is digital automation. Yeah. So when you have all these very complex projects, how can you actually realize them? Yeah? And what kind of steps is necessary for start thinking about, not doing all the drawings in hand or have a person. Yeah. So I worked on Louva Abu Dhabi. I don't know if have you seen the project in Abu Dhabi by Jean Nouvel. Yeah. So it's a big steel dome spanning about 180 meters. And the steel dome, just if you click on the next one, it has layers of cladding on top of it and on the bottom. Yeah. So I'm just going to talk about the cladding layers and the fabrication of the 7,800 stars. Yeah. So if you would do the contract period for this project was just under 2 years. Yeah. And when you work in the Middle East, you get the contract after the 2 years started. Yeah. So they really squeeze you down to the end. I'm sure everybody has worked in the Middle East, and it's not easy. Yeah. So the question is, how could you then automate all these stars? And this is what I was part of. And having a special designer who sat down and said, so, you're going to have all these stars. They're all aluminum. They're all different. There maybe 4 are the same. But then, just to do a manufacturing of all these different, drawings, it's impossible. There's just too many. I think there was There's hundreds and thousands of different drawings. Yeah? So all was automated. Yeah? And the way that it was done, and it's done by a guy called Goswin, he simply sat down and programmed everything. Yeah? And this is the four of the cladding layers. And this is the computer just sitting and actually making each separate aluminium profile, how it was cut, how long it was supposed to be, and a digital file that went straight into a machine that then could manufacture it. Yeah? And this is very important. And this is where we're going to go to. Because if you don't start doing these things, there's going to be other people who are going to do it. And then they're going to be cheaper than you. Yeah? And this is very important. And this is one of the things that drive the agenda of MOTT MACDONALD today, is that we have inside MOTT MACDONALD, we have something that just says, go digital. And we are taking that step as a whole company, 16,000 people. How are we going to transform into an analog world into a digital world? We want to exist tomorrow. We want to have a profit tomorrow. We're all shareholders in our company. We want to keep having that profit. We can only do that by being a step ahead of everybody else. So that's why we have said we're going to be fully digital. Yeah, and it's not going to be an excuse anymore. Yeah? Then we can start talking about what does that mean and how do you do it. And the big question for all of us is like, which programs are we going to use to be fully digital? Yeah? Which kind of software? Which license are we not going to use? Which of the licenses is going to be global? Which is just going to be local? And then again, how do we use that knowledge locally, globally, to make sure that when we have this very expensive software somewhere, we have a sensor, but these are utilized 100% all the time by the whole company and not just locally. Yeah? Okay, moving on. How do you actually then take, because this is interesting, how do you make something that's so complex, how do you make it buildable? Yeah? I spoke, the idea, of course, if you've ever seen Anish Kapoor's The Bean in Chicago, it looks almost perfect, yeah? From the outside. And this is because the radii on the panels on the outside are very big, but if you go inside, it starts to be complex. Yeah? Here we have panels which are both positive and negative Gaussian curvature in the same panel. And the question is, how do you manufacture this? And what you do see is, you see the reason why it is a bit rippled, and that ripple is actually only 1 millimeter in some place, is because it was almost impossible to manufacture these panels so they had the right curvature. Yeah? Okay, so what are the things we need to think of? And you can put this into a diagram, and we looked at this, and I've put these two things in, like when you do complex design, into your geometry, then the applications, which are the drawings, and then the performance, the specification, yeah? And a combination of all these things. And I like to use this analog, and I'm gonna, if I talk a bit about, when you work with Zaha and say, if you want to design a spaceship that needs to go in through the atmosphere, you probably shouldn't get Zaha to design a spaceship, because it'll probably burn up in the atmosphere. So there are some requirements which are so high that you cannot add it and then also add complex geometry on top of it. Yeah? And this is very important. And I'm going to show you why. This is not a scientific graph. It's just me trying to combine three simple things. One is time and cost and performance, and then time and cost and complexity, and then complexity and performance. And just saying, if you have very high complexity in geometry, there's some performance you can't get. Going back to again saying you can't get a freeform complex geometry spaceship flying in through the atmosphere, at least not yet. If you have a lot of complexity, it's going to take a long time to manufacture it, and it's probably going to cost a lot of money. Yeah? And then the last one is time and cost. If you have a lot of high performance requirements, you go over and above what you can actually do, then it is going to cost and take time. Yeah? So going into the buildability, looking at this, I showed you this before, and one of the things I didn't show is that up on top is the door. Yeah? And it's a complex geometry door. It is tilted, and the surface is conical elliptical. You could make it even more complex and make it into a double curved door. But it's actually not really double curved because it's a ruled surface. Yeah? I'm just going to show this door. So I signed up to making 4 of these doors, and they're all different. Yeah? They've never been done before, and everybody who does doors, they know that if the door is not flat, you shouldn't do it. Yeah? If the door is above 2.4 meters, it's not a door anymore. Then it's something else. Yeah? I'm going to ask you a question. how much do you think that door cost? In euros, a figure. It's without the development cost, just the door itself. Somebody have a... Huh? 4,000 euros. Okay, I'm sure, if you can do that for 4,000 euros, there's a lot of... Huh? 40,000, yeah. So the price ended up at 100,000 euros, yeah? And that was without the development cost, yeah? The development cost alone for that door, maybe it's because I'm not a good engineer, yeah, and my engineering team is not very good. The development cost of this door ended up at 350,000 euros. And that was, and when we spent the 350,000, we still hadn't met the performance requirements of the client. The door was still not watertight. And I had to stand in front of the client is legal, and the family, and very rich people, and say, 5 times a year, you're going to have rain on the floor. And they said, well, that's not what we paid for. I said, well, we can do another test, a new door, and spend another 100,000 euros, and maybe it will be a bit better. And this is some of the things, So an architect, they come up with an idea. They say, we want this. And I was foolish enough at that time, said, well, nothing is impossible. I can do everything. Yeah, but there are limitations. It is physically not possible to take a frame and then bend it and twist it, and then take another frame and bend it and twist it, and then get these two to match. There's a limitation in the material. And that just 1/2 of a millimeter is enough that the air gap comes in. So you have a gasket, you try to compress it, but that little change in curvature is enough that the air comes in, which stops you from actually delivering what you promised. And if the performance is not there, the client could say, well, you didn't comply with the specification, we're not going to pay. Yeah? Or you need to find somebody else who can do it. And the problem is that there are limitations in what the material can do. Then you can say, okay, we're going to machine it all out, we're going to do it in solid materials, but then it doesn't have the thermal performance it needs to have. Yeah? So there's always obstacles in all these things. Yeah? Hopefully, with 3D printing, you can maybe start doing these things. Yeah? And this is where the technology hopefully will catch up, and in the future, and this is why we should always push the boundaries. And I think in the future, it might be easier. But at least these doors are very complicated. Yeah? Okay, going back to the glaze link and looking a bit at the ceiling there, yeah? And the installation of it, because I'm just going to show the next picture, which is, how the plates itself and how they're manufactured. The plates was actually done like you do ships, the nose of a ship, yeah? So they actually did it by pressing them, the steel itself, yeah? And what I didn't realize when I looked at this is that when you start hand pressing double curved steel, is that the last 5 centimeters of the steel plate stays straight, yeah? And then when they welded them together, you have a curve and a straight and a straight and a curve, and that is what gave these ripples, yeah? And I didn't realize this. And then the question is, could you have done something about it, yeah? And this is some of these things, when you realize. The good thing is that the architect actually in the end said, well, I like this because it looks handcrafted, yeah? So in the start, they wanted this like fluid view or image, but in the end, he actually said, this looks much better, yeah? Which of course saved me a bit, yeah? Okay. So this is I think some of the last things I'm going to talk about. If you ever have a chance to go and see this building, go and look at it. It's quite amazing. The last thing I'm going to talk about is about the next steps, because this is a journey for all of us. Digital design is on us. When I started at university, that's when email started. And this is not more than 20 years ago. Yeah? So this is moving very, very fast. Yeah? And what the computers can do today, and what they could do 20 years ago, is amazing. So I think digital design platforms, I think open software platforms is the future. Yeah? And you see this if you use Rhino, you use plugins, and all these plugins makes a possibility to develop things much faster. And there are people out there that if you have closed, like some of the things Autodesk is doing, and Inventor has not moved as fast, for example, or Autodesk has not moved as fast as Rhino has, for example. And the possibilities you can do in Rhino today with all the plugins, and how you can connect different programs, yeah? And how you can then start to do interoperability between the different softwares is really, really important. And then you can really start to automate. Yeah? Then, of course, understanding complexity between geometry and requirements is very important. Yeah? And then one of the things I like is like adapting known solutions to new applications, because this should be the first one. So if you start making new solutions to new applications, it's going to be expensive. This is what we tried with the door. Yeah? And then, of course, keep developing new solutions. Yeah? And then I think really understanding capabilities, time and cost. Yeah? Where are the limits in each factory? Like, how much do we want to push the boundary, and what are we going to invest in? What is the return on investment? How long it's going to take before the people in the factory actually are trained to do the things so that the product that comes out at the end of the day actually is fit for purpose, yeah? The last thing, of course, is what I like, is that we have to work together, because if we just work in silos, we will not get there, and I think it's important, yeah? And that ends my presentation. Thank you for your time.